Welcome back to Calculus 2. Today we're going to talk about using the integral to calculate volumes. We'll start with volumes by slicing. This is based on something called Cavalieri's principle. Cavalieri was interested in finding the volume of wine barrels. The problem with wine barrels is that they bulge out. So Cavalieri's idea was to slice it into thin slices. You can approximate the volume of a slice by the volume of a cylinder. A right circular cylinder has volume equal to pi r squared h. If you take the area of a disc-shaped face, pi r squared, and multiply by how far you sweep it, h, you obtain the volume. More generally, if we take the area at some slice at height x, then the volume of a thin slice of thickness dx, the little element of volume, is the area times the thickness. It follows then that the volume, if we start at a and end at b on the x values, will be the integral from a to b of a of x dx. You take an area of a slice times the distance that you sweep it. That gives you a little bit of volume. Add it up between x equals a and x equals b. You get the total volume. Let's do a quick example. Let's suppose we have a square base pyramid, length L and L on each side. It has a height h. And let's find the volume. We'll find the volume by taking thin slices of a very small thickness. We'll measure these slices from the top. So this going down is a positive value of x. Its thickness is going to be dx. But to find the area, we need to know how wide each of these little lengths is. So let's call the length of this side, let's say W for width. Then how big is W? If we look directly on the side, you can see that W is to x as the total height is to L. W divided by x equals L divided by h, or W is L over h times x. It follows then that our element of volume is going to be the width squared, L over h squared, x squared, times dx. And we can find the total volume by adding that up as x goes from 0 to h. L and h are constants in this integral. So we'll have L squared over h squared out front. An antiderivative is going to be x cubed over 3 evaluated from 0 to h. That gives us 1/3 L squared over h squared times h cubed. We get 1/3 L squared times h. L squared is the area of the base of the pyramid. H is the height. 1/3 L squared h is the volume. In a similar way, it can be shown that if you have a base of any shape that has some area A, and you make a weird shaped pyramid like this with height h, with all little cross sections like this, then the total volume is 1/3 the area of the base times the height. I'm going to now discuss the method of disks and washers. It goes like this. Suppose you have some function y equals f of x, and you're going to revolve that around the y-axis, generating some weird shaped object like this. To find the volume of the solid of revolution, what you do is you take thin slices of thickness dx at some x. You'll find these little disks are formed when you make these slices. The element of volume of a little disk is going to be pi r squared h. By Cavalieri's principle, we'll take pi r squared as the area of the face. The radius is f of x. So the area of the disk is pi f of x squared, and the thickness of the disk is dx. So that gives you the element of the volume. To get the total volume, you add these up as you go from A to B. The volume by the method of disks is pi, the integral from A to B, f of x squared dx. For example, suppose I'm taking my function to be 1 plus the square root of x, where x goes from 0 to 1. As you can see, we're taking a vertical translation of the square root function, but only between 0 and 1. We end up with a ham-shaped solid like this. What is its volume? Well, pi integral from 0 to 1, 1 plus the square root of x quantity squared, dx. Make sure you get that middle term when you square out this binomial. 1 plus 2 root x plus x dx. Don't forget that middle term. You square the first term, you do square the last term, but you get first times last times 2 in the middle. This is x to the 1/2, which makes it more amenable to applying the power rule for antiderivatives. So we'll have x plus 2 x to the 3/2 times 2/3 plus x squared over 2. Plugging in 1, we have pi times the quantity 1 plus 4/3 plus 1/2. 4/3 and 1/2 is 8 plus 3 is 11/6, plus another 6/6 gives you 17/6, so we get 17 pi over 6 is the volume of that ham-shaped solid. The method of washers is really just the method of disks applied twice. In this method, you have an upper curve, y equals f of x, and some lower curve, y equals g of x, and you resolve the whole ensemble. You revolve it about the x-axis like this, and you're looking for the volume of the solid between these two curves. So you get the volume is pi integral from A to B. Well, the volume inside of F minus the volume inside of G That's it. As an example, suppose my two curves are f of x equals the square root of x, and g of x equals x squared. X takes values between 0 and 1. The square root of x looks like this, and x squared looks like this. We're taking this leaf-shaped region and flopping that around, generating a solid. The total volume should be pi, the integral from 0 to 1, the outer function squared, which is just x, minus the inner function squared. That gives me x to the fourth. So I get pi times x squared over 2 minus x to the fifth over 5. That's pi times 1/2 minus 1/5. 5 minus 2 is 3/10. That's 3 pi over 10. In our next example, we're going to revolve the curves about the y-axis instead of the x. There's really not that much of a difference. We're going to call the curves x equals y cubed and x equals y, and we're going to look at y values that run from 0 to 1. X equals y cubed looks like this, and y equals x like this. So from the perspective looking on the side, when we revolve this about the y-axis this time, the upper curve is going to be x equals y, and the lower curve, x equals y cubed. You need to get the order right so that you get a positive answer for your volume. We'll take outer curve squared minus inner curve squared, and it's dy this time. So it's pi y cubed over 3 minus y to the 7th over 7, evaluated from 0 to 1. Pi times 1/3 minus 1/7. 7 minus 3 is 4/21, so it's 4 pi over 21. We can revolve around other lines besides the x-axis or the y-axis. For example, suppose we want to find the volume of the solid obtained by revolving the curve f of x equals x squared about for x values between 0 and 1. Then the idea here, you have y equals x squared, but we're revolving around x equals minus 1. So we'll get a solid shaped something like this. The radius is going to be 1 unit plus the height of the function. So we'll get a volume of pi, integral from 0 to 1, 1 plus x squared squared dx, radius squared, pi r squared h. So that's pi times the integral from 0 to 1 of 1 plus 2x squared plus x to the fourth dx, or pi times x plus 2x cubed over 3 plus x to the fifth over 5, evaluated from 0 to 1. We have pi times 1 plus 2/3 plus 1/5. 2/3 and a fifth. Let's see, that's 10 plus 3. It's 13/15. This gives us 28 pi over 15. Next, we're going to talk about volume by cylindrical shells. Or sometimes simply the shell method. The idea goes like this. Suppose we have some piece of curve, y equals f of x, between a and B. And we revolve this whole undergraph around the y-axis, generating a solid with maybe a hole in the middle like this. Here's what we'll do to find the volume of that resulting solid. At x, we'll take a thin slice. How wide? Of course, of width dx. And we'll spin that little slice all the way around, generating a little thin cylinder. We can find the volume of that cylinder by a simple procedure. What we'll do is we'll take that little thin cylinder has a little thickness, and we'll cut it. And then we'll unravel it, generating a long thing looking something like this. We can find the volume of this little thing. Its height is dx. Its width is going to be f of x. And how long it is the circumference around. The circumference of a circle is 2 pi times the radius being x. So 2 pi x is how long. It follows then that this little infinitesimal volume is 2 pi x times f of x dx. To find the total volume, we add these up as we go from A to B. And this gives us the method for finding volumes by cylindrical shells. Let's revolve y equals e to the x squared about the y-axis, x values between, say, 0 and 1. This function ought to strike fear in your hearts because you should be able to recognize that this function has no elementary antiderivative if integrated on its own. That means the fundamental theorem of calculus is out if we try to integrate that by itself. But we're not integrating that by itself. To find its volume, we need 2 pi, the integral from 0 to 1, x, f of x, dx. We get this extra factor of x. If we move the 2 in, you can see the derivative of something plainly lying around. It looks like we're going to need to use the method of substitution. So set u equal to x squared, the thing that has its derivative lying around. Du will then be 2x dx. If x is 0, u is 0. And if x is 1, u is 1. So we've transformed the limits of integration. If the upper limit were 2, u would go to 4 instead. We're going to have e to the u. We're going to have e to the u du. The 2x dx goes away to become the du. This gives us pi e to the u evaluated from 0 to 1. That's pi times e minus 1 as our volume. On our next problem, we're going to take y equals the square root of x minus 2. That translates the square root curve 2 units to the right. We're going to chop this off at x equals 6 and by y equals 0, yielding this region that we're going to revolve around the y-axis. What is the volume? We'll use the method of cylindrical shells. 2 pi, the integral from 2 to 6, the square root of x times the square root of x minus 2 dx, x f of x dx. How do we integrate this? Well, it does look like a job for a u substitution. U equals x minus 2. If u isn't the thing that has its derivative lying around, then u is the impediment. Du is dx. When x is 2, u is 0. When x is 6, u is 4. X is u plus 2. And then we get u to the 1/2 du. We have 2 pi, the integral from 0 to 4. We'll distribute first. We'll have u to the 3/2 plus 2 u to the 1/2 du. We have then 2 pi u to the 5/2 times 2/5 plus 2 u to the 3/2 times 2/3, evaluated from 0 to 4. When we plug in 4, take the square root first. The square root of 4 is 2. 2 to the 5th is 32. Times 2 is 64. The square root of 4 is 2. Cubed is 8. Times 4 is 32. Now it's best to factor out as much as you can first. We can factor a 32 out. So we'll have 2/5 plus a third. That's 6 plus 5 is 11/15. 2 times 32 is 64. Pi times, we said, 11/15. What is 64 times 11? Well, it's 64 and 64. That makes 704. Pi over 15. Next, we're going to try to find the volume of a drilled sphere, kind of like an olive that's had the pit drilled out. Let's suppose that the inner radius of the cylinder that's drilled out is little r, and the radius of the sphere is big R. Notice that the equation of a circle of radius big R is x squared plus y squared equals big R squared. It follows then that the top part of the circle will be the positive square root, r squared minus x squared. If we want to get the bottom part, if we just revolve the upper part from little r to big R around the y-axis, that will only give us half of the volume that we need. So the volume will be double 2 pi the integral from little r to big R of x, f of x, dx. We had to double to get that bottom part. It looks like we'll need a u substitution. We'll bring one of the 2's in here and write u equal to r squared minus x squared. Du will be minus 2x dx. We don't have the minus, so we'll move it over. This gives us 2 pi times the integral. When x is equal to little r, we'll have r squared minus little r squared. When x is equal to big R, u is 0. We have a minus from the substitution. We'll end up with u to the 1/2 du. You need to know exactly where everything went. We'll reverse the order of the limits of integration as we go. When you do, you'll get rid of the minus sign. We're going to have u to the 3/2 times 2/3, and we're evaluating from 0 to big R squared minus little r squared. That gives us 4/3 pi times r squared minus little r squared to the power of 3/2 minus 0. So there's your volume of the drilled sphere. Next, we're going to talk about how to find the length of a curve. So, lengths of curves. Suppose we have a curve described by y equals f of x. On some thin little slice here of width dx, we'll have a change in height by dy. We can use the Pythagorean theorem to approximate the change in the arc length. ds will be the square root of dx squared plus dy squared. We can use this to figure out a formula for finding the length of the whole curve as we go from A to B. First, we'll write this as 1 plus dy over dx squared times dx squared, still under the radical. If we assume that we're marching from left to right on the interval from A to B, the dx squared can come out of the square root as a dx. This gives us an element of the length of the curve, dy dx being f prime. So we get the total length is the integral from A to B of the square root of 1 plus f prime of x quantity squared times dx. There's your length formula, easily derived based on the Pythagorean theorem. We have to be very careful in presenting our examples, since most of these integrals go straight to hell. Let's suppose I have y equals x to the 3 halves. X goes from 0 to 4. Find the length of this curve. Well, the length should be the integral from 0 to 4, square root of 1 plus 3 halves x to the 1 half squared dx, according to our formula here. We have the integral from 0 to 4, the square root of 1 plus 9/4 x dx. This looks like a job for a u substitution. U is 1 plus 9/4 x, so that du is 9/4 dx. Leave a little gap because we have to move this 9/4 over as a 4/9 on the other side. That will give us a 4/9 out front. We're going to transform the limits of integration. When x is 0, u is 1. And when x is 4, u is 10. We'll have u to the 1 half du. You need to know what just happened in every little detail here. We have 4/9 u to the 3 halves times 2/3 evaluated from 1 to 10. When you take a number and raise it to the 3 halves power, that's the same thing as a to the power of 1 plus a half, or a times the square root of a. We'll have 8/27 10 root 10 minus 1. On our next example, we're going to have f of x equals 2 e to the x plus 1/8 e to the minus x, where x will run from 0 to the natural log of 2. Find the length. The length is the integral from 0 to the natural log of 2, the square root of 1 plus the derivative. The derivative is 2 e to the x minus 1/8 e to the negative x squared dx, 1 plus f prime squared. To see what to do next, we need to FOIL things out. We have 1 plus 4e to the 2x. For the middle term, don't forget first times last times 2. 2 times 2 is 4/8. Gives us a half, but it's minus. E to the x times e to the negative x, you add the exponents. You get e to the 0, which is 1. And then the last term squared. All that under the radical times dx. There are two like terms, 1 and minus 1/2. That'll give us a positive 1/2. And what's left over is a perfect square, except instead of minus, you'll get a plus. We have the integral from 0 to the natural log of 2 of the square root of 2e to the x plus 1/8 e to the minus x quantity squared dx. The square root and the square will cancel, and then we can integrate term by term. We have 2e to the x minus 1/8 e to the minus x evaluated from 0 to the natural log of 2. Plugging in the natural log of 2, e to the natural log cancels out, so we end up with 2 times 2. If we have natural log of 2 times a negative 1, the negative 1 goes up, and negative ln of 2 will be ln of 2 to the negative 1. That's a half. Times an eighth is a 16th. And then we have to subtract what we get when we plug in 0. That's 2 minus 1/8. So we have 4 minus 2 is 2. Negative 16th plus an eighth is positive 1/16. That's 33 sixteenths. In preparation for our next example, I would like to review a little bit about hyperbolic trig functions. The hyperbolic sign, which is pronounced sinh of x, is defined, and that means because I say so. Definitions you accept, theorems you prove. E to the x minus e to the minus x over 2, whereas the hyperbolic cosine of x is, and that's pronounced cosh, e to the x plus e to the minus x over 2. Notice that the derivative of sinh is cosh, and the derivative of cosh is positive sinh. Also, we have a little bit of a theorem. Cosh squared x minus sinh squared x equals 1. Things are always just a wee bit off for these hyperbolic trig functions compared to the circular functions. Let's prove this. We'll take hyperbolic sine, this left-hand side, and square it. That's e to the x plus e to the minus x over 2 quantity squared, minus e to the x minus e to the minus x over 2 quantity squared. Both terms have a factor of 1/4 after we square the 2 in the denominator. We'll have e to the 2x, first times last times 2. E to the x times e to the negative x is e to the 0, which is 1, plus the last term squared, e to the minus 2x, minus on the second term, the square, e to the 2x minus 2 plus e to the minus 2x. A lot of things cancel. E to the 2x's cancel, e to the minus 2x's cancel, and we're left with 2 minus negative 2 all times 1/4. The answer is 1. On our next problem, we're going to look at x equals cosh of y, where y takes values between 0 and the natural log of the square root of 2 plus 1. The length will be the integral from 0 to the natural log of root 2 plus 1 of the square root of 1 plus the derivative of cosh, which is sinh, squared. One plus sinh squared is cosh squared by the theorem we just proved. Cosh is always non-negative. When you take the square root, you'll always get plus. So we're integrating from 0 to the natural log of the square root of 2 plus 1, cosh of y dy. Well, the derivative of sinh is cosh, so the integral of cosh is sinh. It's a sinh. We have the hyperbolic sine of y evaluated from 0 to the natural log of the square root of 2 plus 1. So we get sinh of ln of root 2 plus 1 minus sinh of 0. Hyperbolic sign at 0 is 0. E to the 0 minus e to the negative 0. 1 minus 1. 0 over 2, you get 0. The question is, what is the hyperbolic sign of the natural log of root 2 plus 1? We have e to the log, root 2 plus 1, minus e to the minus log, root 2 plus 1, all over 2. The e and the log cancel easily in the first term, but not in the second term. You have to bring the negative 1 up first. Then you can cancel. I'll put this 1/2 out front. We'll have root 2 plus 1 minus 1 over root 2 plus 1. We'll rationalize the denominator in the second term by multiplying numerator and denominator by the conjugate. We'll have 1/2 root 2 plus 1. In the denominator, you'll have 2 minus root 2 plus root 2, and then minus 1, which gives you 1. The numerator is root 2 minus 1. Root 2 minus root 2 will cancel. 1 minus negative 1 is 2 times 1/2. The length of the curve is 1, which makes us very happy. There's only one more topic today, and that is surface area for surfaces of revolution. Suppose we have some curve, y equals f of x, between A and B. We're going to revolve that about the axis, generating some kind of a hand-shaped surface. We're only looking at the surface this time. We want to calculate the total surface area, so at x we'll take a thin slice. Of width dx. The arc length is ds, which is key here. We're going to generate a little band. We're going to take that little band and cut it. Here's our little band. It has a little length like this. It goes around. We're going to cut it and unroll the thing. We're going to roll it out. And then the area of that little band will be the piece of surface area. The element of surface area then will be the width, ds, times the length of this whole thing. The length is the circumference, which is 2 pi times the radius, which is f of x. Now ds is that arc length. The surface area then will be found by integrating the element of arc length from a to b. It's 2 pi f of x times this ds. ds was the element of arc length. That's the square root of 1 plus f prime of x squared dx. And that's the formula for the surface area of the surface of revolution. So for example, suppose I have f of x is 2 root x. X will run from 1 to 3. Find the surface area. We'll have 2 pi f of x ds, which is the square root of 1 plus the derivative. Remember that the derivative of the square root of x is 1 over 2 root x, but we're multiplying by 2. So we'll just end up with 1 over root x squared all times dx. We'll have 4 pi, the integral from 1 to 3, times the square root of x. The square root of x can be brought in. The square root of x can be brought in as x times 1 plus, here we have 1 over x dx. We'll end up with x plus 1 under the radical. we'll have 4 pi times 2/3 x plus 1 to the 3 halves evaluated from 1 to 3. That gives us 8 pi over 3. Plugging in 3 plus 1 is 4. Take the square root first. 2 cubed is 8. When we plug in 1, we're going to get 2 to the 3 halves. That's 2 root 2. And let's just leave it. Suppose we're trying to calculate the surface area of a little spherical cap, kind of like a yarmulke, I guess. Let's suppose that the sphere has radius big R, and the thickness of the cap is h. That means we're going to go to r minus h along an axis. What we could do is we could take the formula for the circle, square root of r squared minus x squared, and just take the portion from r minus h to r and flop that around the axis, generating this surface. We'll get the surface area is 2 pi, the integral from r minus h to r, and it was 2 pi f of x. That's the square root of r squared minus x squared. Square root of 1 plus f prime squared dx. We have 2 pi, the integral from r minus h to r. We can bring this in. We'll cancel first. The negative gets squared away. We'll have the square root of r squared minus x squared times the quantity 1 plus x squared over r squared minus x squared dx. When we multiply under the radical, we'll have r squared minus x squared here, and on the second term, the r squared minus x squareds cancel in it, so it's just plus x squared. The x squareds cancel. Square root of r squared is r. We'll have that value r times the length of the interval, which is h, and that's the surface area. We've had a number of different formulas today. We had disks giving us the volume, pi integral from a to b, f of x squared dx. We had washers, 2 pi integral from a to b, x, f of x dx. And we had the length, integral from a to b, square root of 1 plus f prime of x squared dx. And we had the surface area, which is 2 pi integral from a to b, f of x square root of 1 plus f prime of x squared dx. You're going to need to know these for the exam.